Part 2. In the 80s, it generally believed that congenital abnormalities affect about 5% of the nation's children. Some people believe the increase of number of chemicals in the environment has led to an increase. A recent study examined 384 children and found that 46 of them showed signs of abnormalities. That's our sample. Is this strong evidence that the risk has increased? Do a hypothesis test, confidence interval, and then discuss type 1 and type 2 errors. All right, so I typically do 4 steps in my hypothesis testing. So step 1 is basically what we are doing, right? Boom, boom. We'll make that bold there. I'll italicize that. Okay. So what we were doing. So this is the parameter of interest P. P is the proportion of children that have congenital abnormalities. Okay. So what do we need to do? This will be a one sample z-test for the proportion of children that have congenital abnormalities. There we go. All right, so we need our hypotheses. So it's proportion, right? It's a percentage up there, right? It's proportion, and we're going to use z-test for these. Okay, I'm going to do t-test and some others later on in the chapter. All right, so we have our null hypothesis, which is h sub 0, and our alternative hypothesis, which is h sub a. Some books use h0 and 1, some use hn and ha, depends on the book. 0 and a tend to be the common ones, but not always what is used. There's definitely always two, no alternative, right? So we assume 5% because that's what the research says, but we want to prove, or we think it's more than 5%, right? All right, so that's what we want to do, and then it's a question of, at that point, can we do it? All right, so we're going to do a bold there, italicize there. You don't need to write these little italicized ones that I'm doing. I'm just doing that for the sake of the lesson. Okay, we'll do a little bit of math here. So n times p, oh, that's too big, times p equals, that's what, 384 times 5%. Oh, times 5%. That would be 19.2, right? And then we can copy that. Copy. Paste and times q, right? It's the number of samples passing and failing. So this would be 95%. So that's 364.8, right? So both of these have more than 10, so that's more than good. That means we can do it, right? So at that point, it's a matter of our hypotheses. No, I'm sorry, not hypotheses. The mean and the standard error. All right, so our mean of the proportion P oops, crap, there we go, I clicked on the wrong thing. Need a little hat above that, there's a little hat. Okay, so that's what we get there. I'm going to take this, copy, paste, and change that to the standard deviation. Okay, equals, and the square root ratio, so we get 0.05 and 0.095 over 384. Okay, so this says we can do it, so these are our values we're going to use. So, whoops, what's going on there? It is less than 10% of the population, right? Obviously 384 is less than 10% of the population, so these samples are independent. So replacement is not really an issue because it's just a small number of the overall population. It doesn't matter. And there is no reason to assume these samples were not selected randomly. Because if either of those weren't true, you couldn't do it basically, right? So those both have to be true, right? They're independent, it's actually random, and then it needs to pass this, right? So that means we can do it, right? All right, so step 3, we'll actually carry it out. All right, so do it, basically, right? So carry out the operation / statistics, right? Statistics, there we go. Okay, so I'm going to bold that and italicize that. Okay, all right. Math type, so we want, all right, p hat equals, so p hat, all right, so I believe it was what, 46? Let me double check that. Yes, our sample had 46, right? Out of 384, found with the abnormalities. Right, because that's our sample, right? It's not p, because p is the population and p hat is the sample, right? Which we compare. So my z is a ratio, and we have the 46 over 384. Ooh, that's not it. 384 minus 0.05, right? And then this right here is the square root, right? Ratio 0.05. 0.95 over 384. Okay, okay, right? Because you have the p hat minus p, correct? Over the standard error, which is this right here, standard error. Okay, which I believe we have back here on a formula sheet, right? Somewhere. I think it was in the prior lesson, to be honest. Yeah, it's prior lesson. Okay. Where am I at? Right there. Alright, so now I can do the area. Alright, so area equals 1 minus the normal dot distribution. And we want to do the z, comma 0, comma 1, comma true, which gives us an approximate value. Okay, let's think about what we're actually doing here, right? Nope, that's not what I want. I want this tool right here. All right. Oh, where am I? There we go. Okay, so we have this little normal curve right there. We got a little right? So this is what, 0.05? Right? So we have a z-score which is, it's going to be what, negative, I think, right? So let's get a z-score over here somewhere, right? Alright, that's the z-score we have. The problem is if I do this function, that's going to give me this area. Because the function in the spreadsheet works left to right. It's going to give me that area, which is not what I want because we're doing a greater than. So we actually want all of this area over here, correct? Right? So 1 minus will flip that over basically. Okay? Alright, let's see in the spreadsheet how this works out. So we need a spreadsheet here. Okay, so let's zoom in a little bit here. We'll say p hat equals q hat equals, right? The standard deviation. Oh, I got that wrong. Equals, and then the area equals. Okay, we'll shove those to the right. Boom, boom, boom. Oh, that's not what I wanted. I want this one. There we go. Okay, so that's 46 out of 384, right? So if I subtract 46, that'd be 338, I believe, right? 338 out of 384, right? Because those have to add up to 1, right? So I do this plus this, I get 1. So I did that right. Okay, I can do math. All right, so equals the square root, parentheses, 0.05 times 0.95 divided by 384, close paren. Okay, we got it. Oh, we forgot z. We forgot the z. We got to put that in there, right? We got to put the z, and then we do the area. My bad. Okay, so the z, right? So the numerator is, if you kind of think about it side by side here, right? It's p minus this, right? So the p minus 0.05, that's the numerator, right? Divided by, divided by this right here, correct? Because that's that whole thing with the square root we did. So there's our z value. That was a positive z value. I lied then. So again, I didn't do the math in my... Oh yeah, 0.11. Okay, that's why. Because I was thinking the other way around. Because that's 5%, that's 11%. That gives you a positive z value. All right, I'm wrong. So when I drew the picture, I for some reason flipped those in my head. So the reality is my z is way up here, right? Because that z is a was what, 6 point something or 11 point something? I forget. Let me pop it up. No, 6 point something, right? So that's 6 point something up here. So that's a positive, right? Because this is z equals 0 in the middle, right? Which, as far as x goes, right, or p, I guess say, is 0.05, right? So the problem is if I do this function, it's going to give me this area, which is not what I want. I want this area over here, which is why I do 1 minus, right? Because I want the greater than. The greater than means it's going this way from the z, right? Okay, so let's change this. We can put this in here. We don't really need it because we use the exact value anyways. Say 6.275. 6.275 ... right? That's all we want. Okay, so we do the area now. So 1 minus normal, oh, I didn't put it equals 1 minus normal dot distribution. It pops right up. It actually tells you got to put the x in there, right? So that's actually the z. Because we're doing it in terms of z, comma 0, comma 1 is what you use for z. You don't need to change them from standard. And then comma true, which means to cumulatively add up all the area, right? Okay, so that is not in scientific. That's in scientific. We want to change that to a number, right? And just keep adding more decimals. I don't know. That seems good, right? That's probably more than we need anyways, to be honest. We could probably go right to there. That's probably fine. So that's what, 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros, right? I got that right? 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. Okay. All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9. Was it 175, I think, right? Correct? Yes. Well, ish, right? ... right? So that is the approximate p-value, right? The approximate p-value. Okay? That's the approximate p-value. All right. So we can minimize this for now. So carried it out, this is the p-value you get, right? So the area under the curve is the p-value. Okay, so we did it, we carried it out. Now we have to analyze now. Step 4, right? Analyze the findings, or should be your findings, I guess. Findings and make conclusions. Okay. Make that bold. Make that italic. Okay. So basically, the p-value is value is less than the alpha, which we're going to set as 0.05 because it wasn't specified, so we're going to reject the null hypothesis. Okay, so if it's not specified the alpha level, right, to use, basically you use 0.05, which is basically known as the Fisher rule. The Fisher, you can find out through the books. There's a guy who figured out, he just basically decided at one point that 1 over 20 was good enough. So if not specified, this book tends to use the Fisher rule, which is 0.05 for alpha, right? So if you remember the rule, if it's less than alpha, you reject. If it's greater than alpha, you do not reject, basically, is the rule. Okay, that's in Stats 1 and in Stats 2. It's in this book in both parts. The first half of the book is Stats 1. The second half of the book is Stats 2, right? Okay, so that means, basically, our sample proportion, because our sample is a proportion, is significant, right? And not likely to occur. What does that mean? So, if we didn't reject it, we would be. If we did not reject it, that means that whatever sample we have is one that's common, and there's nothing out of the ordinary. Just accept reality of the 5%, right? But we found one that was significant, right? Which means we can reject this, and it's not normal, right? It's right. It's not likely to occur, right? So this is an abnormal sample based on what we're saying is reality. So there is enough evidence to reject the null hypothesis, which is what we did. You must assume the null hypothesis is likely false, right? But we did not prove it false, right? So we used to believe the population was 5% abnormalities, so we didn't prove it. We just found enough evidence to say it's likely not that, because this whole unit is on inference, right? We're inferring as to what the answer is. You don't absolutely ever know anything, right? You're just proving what you think it is based on the statistics, right? It's best guess. All right, so it is likely that the number of abnormalities has increased. That's what we found. Otherwise, it would just be the same. What was found was not in the expected range of outcomes. Okay? So our sample was not in the expected range of outcomes. It's outside of that, so therefore we found enough evidence. Okay, so let's do the confidence interval and compare here. Confidence interval. Okay, let me copy that from the previous section. Bold. Okay, so we're going to copy and paste. Okay, so there's this. Okay, so we're going to say, for the confidence interval, we're going to say that alpha is 10. Oh, that's not why did alpha go here? Come on, alpha. Alpha is 10. And you're like, why is that? And then we'll do z subscript. I'm going to do a little sideways ratio. I think this one here is probably good. Alpha divided by 2. Okay. Equals normal dot inverse. And we're going to put 0.95, comma 0, comma 1. And this will be approximate. Let's talk about this. Okay. So the hypothesis test was 5%. Okay. Hypothesis test was 5%. Right, which is this right here, right? So okay, so it was looking for this 5% here. Okay, but the problem is when you do a confidence interval, it's plus or minus, right? So you actually have 5% here also, so which means this one plus this one is 10%. Okay, so that's why it's alpha divided by 2. You know what I'm saying? So why are we looking for 95? Because here to here is 95. That's why. Okay, because if you're doing a one-tailed test, which is what we're doing, right? Because we're doing a greater than p is greater than, that's a one-tailed test, which means we're looking for this one. If we're doing the other one-tailed test, we're looking for this one. Okay, if you're doing a two-tailed test, which is this, and you're looking for both, then this alpha will match the alpha to the hypothesis test. So the alpha for the hypothesis test and the alpha for the confidence interval only match if it's a two-tailed test, okay, which is this one here. Otherwise, this is not going to match that, okay? All right. Where is the spreadsheet? There it is. Okay. Excuse me. Okay. So Z alpha 2. We'll call it that. How's that sound? All right. So normal dot inverse, right? 0.95, comma 0, comma 1. There we go. About that there. 1.6648, whatever it is. Right? 1.6448 dot dot dot. I think that's what we got. Okay. All right, let's do our confidence interval now. So we have this ratio, which is the 46 out of 384, right? The rest of this, I think I'm just going to keep it as is. I'm just going to keep that as. So this goes here, right? That goes there. That goes there. This one is the Q, so that'd be what, 338? 338, and then this would be 384. 384. And then we can copy that over. All right. So basically what we're saying is the true population is between these two, right? Which is basically, there's our sample, and then the margin of error. The margin of error, correct? Okay? Plus or minus the margin of error. So the true answer is within this range of what the population is. Because who knows? Is our sample right? Is our sample wrong? Who knows? But it's going to be somewhere around the sample is what we believe. Okay? Okay, let's go to the spreadsheet now. Okay, so we have the P, we have the Q, we need the N, right, which is 384. That's the only thing we don't have. Oh, why did I do that? I don't know why I did that. Okay, so the left side, right, is P minus Z times, right, the square root, right, and you have P times Q divided by N, right? So you look at the formula again, right? You have the P, which I put in first, minus the Z times the square root of P times Q over the N, right? Okay, so what I'm going to do is I'm going to copy this, copy, and then paste it in this box and change that to a plus. Because it's the sample plus or minus the margin of error, so it's above and below, right? So those are our numbers there. Okay, so let's go back and write those down now. Okay, so 0.092535, I think is what it was, right? 35, that's good enough. Is less than P is less than 0.147048 dot dot dot. Let me just double check. 0.4892. Okay. All right, so that's our confidence interval. So we think the true proportion is between here, basically. That's what we think. So this is a 90% confidence interval, basically, is what we just found. Okay. All right. So what do we notice? Well, our original value was 0.05, correct? That's what we thought, the 5%. Is the 5% in this? Well, that's 9%, that's 14%. So 5% is over here, right? It's not in the confidence interval, right? Which makes sense because we rejected, because this is our null hypothesis, basically. And we rejected that, which is good because we found it's actually outside of that, right? So our hypothesis test matches our confidence interval, basically, because we rejected, which means it's not in the confidence interval. Okay? So we did the correct thing is what we found. So, all right, type errors. That's the last piece. Type errors. So we have, let's make that bold. Okay, we have alpha, and we have beta. Beta. Okay, so what do each of these mean? That alpha is the probability. The probability, you will determine the abnormalities in children is more than 5% when it was actually 5%, right? And beta is the other, which would be the probability you will determine the abnormalities in children is 5% when it is actually more than 5%, which means we failed, which means our hypothesis and our confidence interval failed, basically, right? Neither one of these cases, type 2 or type A. So this might be a type 1 error because we did reject the null hypothesis, right? And it may be true, right? So we decided to reject it, but it might be true, right? So we rejected it, which means we're saying it's more, but it might actually be 5%, right? So that's because, again, this is inference. We're never absolutely sure, right? This is unlikely. The type 1 error is unlikely. That's what I should say, unlikely, because the p-value is very small and the hypothesized value of 0.05 of 5% is not in the confidence interval, right? So if you look, we had gotten 0.0000001. That's like 90175. That's a very small p-value. You know what I'm saying? So if it was close to 0.05, that'd be one thing, but it's not very close. So it could be a type 1 error, but it's not very likely, basically. Okay? All right, so I did some other ones in here. So this one here is about a medical school, basically, and applicants who admit fall. Okay, so this one we believe is less than 46%, right? But traditionally it was 46%, so we went through the same steps. But here we found a p-value of 19, right, which is more than the 5% default. It can be something else than 5%, but so we do not reject it, which means this sample is not significant. It's likely to occur. We didn't find enough evidence to say otherwise, right? And if we do the confidence interval, which I did here, I got between 36 and 48. And if you notice here, again, this is 90% confidence because the alpha here is 5. So this is 10 because the confidence interval is 2 tailed. This is only 1 tail, right? The original value is 46. 46 is inside of this confidence interval, right? Which is a likely thing to occur. The 46 is in there, right? 46%, which not rejecting makes sense. This is saying that it must have been in the confidence interval, which we showed it is, correct? So in this case, it could be a type 2 error, right? Because we did not reject the null hypothesis, although we might have been wrong. But again, we got a p-value that's pretty high. That's not even close to 0.05, so it's likely not to be true. Okay, and these are two-tailed, so that's not equal to. Not equal to, and this one is a not equal to. Okay, so what you'll notice in these cases, it's 5% for alpha for both of these because they're both two-tailed, basically. Because the confidence interval, because we're saying not equal to, so, right, we believe the answer is here, but it could have been here or here for a two-tail, right? Because it's not equal to, it could be too much or too little, basically. And what you notice in both of these cases that I did, so this one is 34, right? What you'll notice is 34 is in the confidence interval, right? Which means we did not reject it, right? So that means the hypothesis test matches the confidence interval. However, 34 is really close to that. So this might actually be a type 2 error because it's so close, right? And look at the p-value. It's 0.054. That's really close to 0.05. So this might actually be a type error. We don't know. It's so close, it's hard to tell. Right? And here, we think it's not 31. Okay. So what happens is, if you look at this, wait a minute, 31 is just outside of this, but just barely outside of it, correct? So yeah, we did reject it because it is outside, right? But that is really close to 0.05 for comparing to the alpha, isn't it? So we rejected it because it's outside the confidence interval, and the hypothesis test is not close to that, but it's really close. So this actually might be a type 1 error because it's so close. Okay? All right, that's the end of part 1.